All right. Let us see. All right, so we managed to get this to work. So let's keep going. Okay, now at some point here, we should start actually inserting Wolfram model things in here and see if they work.
Mm-hmm.
So do we want to...
Would you like code for that?
Yes.
Okay. I believe as long as you have the graph.
Actually, hold on, let me just do something here. Let's just do you know, for the cellular automaton case, we can at least get the state evolution function for this case. For the case where it's just like that, where it's an elementary rule.
Mm-hmm.
Why don't we just do that one? So that one, the state evolution function, it breaks the thing into tuples, does it not?
Right.
And then for each tuple, yeah, I think that's what that other code was doing. So let's just break it into, so here, it breaks hash into tuples like this. Then for each one of those tuples, it applies You know, I have a feeling that my code might have been cleverer than this. Can you see what on earth that's doing? Look, I suspect the core of this thing is exactly what we want.
Okay.
I don't know what that union is doing. So let's just do rules 170, 240 here. Okay, look at what that did. Did that do the right thing or not?
Okay, so I had one where it did both. Should that be allowed?
Not clear. What is this code doing anyway? Yeah, what this is doing is it's doing the whole gulp. And then I think it's threading through each of the outcomes. I don't think that's correct. I don't think it's correct. I think it should be doing one at a time, right?
Right. I mean, it obviously isn't correct because it's merged two branches of the multiway system. That's what the last element is, right?
Yeah. Okay, so then we partition 3-1 here, and then for each of these, we map, yeah, and then we have to tupulate the whole thing. Right, for each of those, we map cellular automaton What the heck are we doing with the boundary conditions? We need to have something which extends the boundaries, right? So that we pick something off the end. Could you look up how to do that? I can't remember how to do that. Did you look that up? How to do?
You're basically asking how to do transmissive boundary conditions.
No, I'm how to do periodic boundary conditions. I just want to extend at the ends. See what I'm saying?
Yeah, right. So you want a pad left, pad right that does some form of boundary condition. I thought you said you wanted.
Let's do periodic. It doesn't matter. It doesn't.
Okay.
Yeah. I think periodic is fine.
I can't see an immediate way to do it, but didn't we deal with this case in when we implemented sequential cellular automaton?
Yeah, we probably did.
If you have the code for that, we can probably find it.
I know how to do this. Okay. -1, 1 for the overhangs. KL, KR. All right, I claim. Well, let's just give it, see whether it even has a chance. Let's look at this and then apply that to list 0, 0, 1, 0, 0. Oh, it's going to need rules as well. Okay, let's do this. That actually has to be mapped. But that thing is the successor of an individual state, isn't it? The state evolution function is the successor of an individual state, I believe.
Right.
Okay, now, given this, what we have to do is to find all possible
macroscopic states.
No, all possible tuplings, all possible threadings through here.
Okay.
And isn't that just tuples of this? Okay, so that has all zeros in it. That is a threading. So I'm really kind of confused by what this is doing. You get what I'm saying? That has the all zeros case.
And it also has the merged case.
Oh. You know the problem? The problem is that this should only be picking one of these things, right?
Mm-hmm.
So it needs to map over here. It needs to take that original Okay, so what's it doing? It's taking this and it's replacing one of these at every step. See what I'm saying?
Yeah, right.
Isn't it the case that the upper one of these is just one rule? Isn't it the case that we can get I think the mistake is that tuple's there. I think we can do this. Okay, so given a state, the rules, let's say 172.40, and a state, okay, that correctly gives us all the choices. But now, yeah, this is wrong here. Okay. At each step, a single application. Well, actually, these are different models, aren't they? I mean, what the heck is a non-deterministic cellular automaton anyway? It's a non-deterministic sequential cellular automaton. Yeah, a single application of the rule is done at some location. At each step, no, at each step, new states are generated by all possible single applications of the rule at different possible locations, of the rules at different. So wait a minute. So there's a version of this. It's not so clear what this means. Look, because this is.
I don't know. My picture of it was simply it's what you get when you evolve a cellular automaton without keeping track of history, without keeping track of the previous state.
What do you mean? But where you update every cell separately, right?
Right. It's like so with standard CA evolution, you need to keep track of two states. If you say that we can't do that, we can only have one state that we keep track of at a time. The non-deterministic CA is the most general way of doing that.
And then you're just zapping different points in the cellular automaton.
Exactly.
So All right, fine. So then this code is wrong.
I would think of it. I don't know. Non-deterministic doesn't seem quite right to me. I mean, I know what it mean. I know what you mean by that, but for me, it's something more like a historyless cellular automaton.
Well, what it really is,
instantaneous.
It's really a multi-way cellular automaton is what it is. Because that's what we're going to generate here. We're going to generate the multi-way states here.
Right, but cellular automaton, just like substitution system, means something where you have, in effect, you have a knowledge of history. I don't know. Yeah.
Yeah. Well, this is wrong anyway.
Yeah.
I think we're getting off track here, but since we're so close, we might as well just finish this. Okay, so this is what we get by doing that. So what we want to do is pick every individual one of these, but otherwise leave the state unchanged. Correct?
Right.
Okay, so how do we do that?
It would help if we knew the. Well, no, okay, no, actually, never mind.
So this is the original state. And
so we want to do a replacement at the part specification given by the index of that list.
Single update cellular automaton. I mean, this is really the multi-way sequential cellular automaton.
Mm-hmm.
Otherwise known as the non-deterministic multi-way cellular, non-deterministic sequential cellular automaton. Well, I think let's call it multi-way cellular automaton for now. Okay, so take a single step there. Let's say rules and state. Just a single state. Okay. So this gives okay. So that is going to give, yeah, it's a list, isn't it? All right, so that's going to give a list like this. And so what we want to do, we could do it we're map indexing. I claim it could be a map indexed of replace part state #2 sub 1 arrow hash at onto that transposey thing at level 2, I claim. How do you feel about that? So it says multi-way cellular automaton step of rules, say 170 to 40. And I think we need a catenate at the end of that. What do you think?
I mean, we need to union it, but I think that's okay.
Yeah, but unionization is a separate operation.
Right. Right. But that looks valid.
Okay, so here
we still have the zeros case. Should that be happening?
How does it happen?
I think it's because as I mentioned in the last call, I think that if you just apply to the center tuple, both at least 170 and I presume 240 as well, will map 010 to 000.
So you're saying that we don't want to have oh gosh, what are we trying to do here? So that the triple, right? Well, okay, let's not get distracted on this. This isn't right yet. Okay, but I mean, wait a second. So the triple wants to go. We replace a given triple by something. I think this is right. I mean, I don't see why. I don't think this is wrong. I mean, we're taking a triple,
right? I mean,
and we're applying a rule to it.
Yeah, it's doing for the CA case exactly what what is being done in the substitution system case.
All right, so fine. So then this is okay. So here so the state equivalence function is the same Q thing, right?
Mm-hmm.
What do you think about this? I think with the rules as we've defined them, it's correct.
Right. It looks okay.
So let's look down here at one of these guys. Oh, for goodness sake. Well, let's see what this is like. So the predecessor well, that's at least correct that the 0, 0, 0 thing has it as a self-predecessor. Right?
Mm-hmm.
All right, okay. Not obviously wrong. Okay. Well, let's go on one or two more steps, and then let's go put in the Wolfram model stuff. Okay, constructing a complete traced evolution. Oh my gosh, what's all this stuff? So this is probably the innards of a okay. All right. So what is a traced evolution? Multiway system substitutions. All right, so let's evaluate this. Okay, so now let's get a rule here. Okay, so that is now a certain format. That is in fact exactly giving what we want for our evolution.
Right, it's giving the rule and the part specification on the substring.
Right, in what form is that part specification being given? Because what we actually want here, okay, so how is this going to be used? We're using it here. Oh my. Okay, so down here, okay, what did we say we wanted? We said we wanted oops, where did we put that? Oh, here. State event function and state event evolution function. Okay, so this is a state event evolution function that we're getting there, right?
Right.
And what we said we wanted form for the an event is specified by rule comma rest, where rule is a transformation rule instantiated for the particular location where it is applied, and rest is a specification of the remainder of the state excluding the part to which the transformation was applied. Okay, so we might want a property here. Oh yeah, the list of all events that occur at each successive step. So that's exactly what we're looking for here. Right?
Right.
Okay, so now we need to know what so the thing we need over here is okay, so based evolution. Okay, so the first case here is the state event function for strings. For strings and lists. Okay, so this is SS state event function for a substitution system. Well, basically for substitution systems. Let's simplify this to SS SEF. Well, SS events. And that's going to take a rule and a state. And it's going to give us, okay, that's this thing here, I believe. That looks incredibly complicated. Seems to me we should just rewrite that. Because the form we want to give it in, remember, is transformation and prefix suffix. Is that right? That's what we'd agreed to do for this case.
Yep.
Okay. Okay, so given an individual state, we want to find all the places where the left-hand side, that's either the string cases or the sequence cases, where the left-hand side of the rule, right? Maybe we should do the string case first. Okay. So it's string cases in state of hash, well, of like, let's say first of hash onto rule. Actually, we could even do this. It doesn't really matter. We can do this for a single rule, I believe. And we can map it over rules. Make sense?
Mm-hmm.
Okay, so that tells us where the left-hand side of rule appears. No, it doesn't tell us where it appears. Oh, shoot. I mean, there's a certain argument that we should just use this code, except we don't know how to generalize it for other things. Help. Okay. Are you alert here?
Yeah, I think so. If you have a specific question.
Well, I'm trying to figure out what to write here. Okay, so look, let's look at this code here.
Right.
I had a version of this code, and then Max wrote this version. What is the character evolution causal graph? Gosh. We can kind of get rid of this. Well, do you want to try and put in, I mean, maybe we should let Max help with untangling this, because I think he's, unless, okay, can we see, okay, how obvious is this? We want to get something which is the transformation, the prefix, the suffix, right?
I can write that if you want, but I think it would be faster for me to just do it myself than it would be to understand someone else's code.
Yeah, I agree. Well, should we write it together right now? I mean,
it's up to you. I don't know. Yeah.
You think it's more efficient for you just to write it?
No, it's up to you.
Okay, let's try and write it together. So then you have to actually be paying attention, because I'm okay. So what we're trying to do is we're trying to get both the, if we get string position of this, right? That will give us the positions of all those things, right? And then, okay, I think this is as simple as the following. Okay, I think this is simply rule, and then we want to take up to the first position and
all of everything from the last position.
Right, so we want a string take of state, comma, first of hash, -1. Do you agree?
Yes, I think so.
And then we want a string take or string drop. Actually, what we could do,
just drop the middle bit?
No, because then we'll have, then the two sides will come together.
Okay.
String drop from last of hash onwards. No, that's not right. Up to, yes. String drop up to last of hash, right? Okay. So string rewrite event, I claim is that. Okay, so then the full version of this is string rewrite events has plural rules and plural states, right?
Mm-hmm.
So I claim that that is mapping string rewrite event of the rule mapped over a state S and then we catenate that, and then we take the function S and we map that over states, and then we catenate that. Okay, let's see how convincing this is. Okay, so string rewrite events is, let's say, what should we use? Just use this one here. Okay, that's rather uninspiring.
I suspect that's out by 1 errors.
String position. Oh, no, 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 no. It's correct. It's correct. Because
Right.
there's nothing left.
Right. Yep. Okay. There we go.
All right, let's go. So like B goes to AA. Okay, B goes to AA, and what's left over is AA and A.
Yeah, this looks right.
Okay. All right, while we're at it, let's do list rewrite events. Okay. Okay, so I reckon that that's literally just take and drop and position, but for safety's sake, we want to make that position at level 1. Oh no, it's sequence position, isn't it? Right, because it's a run that we're wanting to.
Right, we need, yeah. But hang on, do we want sequence? Oh yeah, no, okay, yeah, yeah.
Okay, so now
Wrong syntax, other way around.
no, it's rules and state.
Rule states. Why is that one of values?
Oh.
What, why have you got two?
I got two thingies there.
Arguments. That looks right. But with, wait.
That's right.
Yeah.
That's right. Okay. All right. So that's then the format. The transformation prefix suffix is the format that goes into this creature here.
Right.
Although it's not obvious that traced states list is actually a thing we care about. Let's see where traced states list is used. Okay, so what does trace states list return right now? I think we just got a really brain dead format for this right now. Right, so what we want to return instead is essentially exactly what we've now been giving, right? But then everything that uses trace states list is going to have to be modified.
But not by much.
Well, let's find out. Okay, so the next thing we want includes step number. Oh shoot, what's that?
It's adding a timestamp.
Yeah. Well, I'm not sure what the event rule specification is doing. Let's find out what that is. That's something we don't care about. The step number for each event might be useful. What do you think?
I think so, given that it's non-trivial to reconstruct it from the information that's given.
All right, where should we put that in? Trans prefix suffix, and then what? Should we put it after that?
Why not before? I don't know. Step
before
number
what?
Step number transformation.
You mean as the first element? Or we could put it as a rule. What do you think? Like that?
Okay, yeah, that's okay.
Okay, all right, let's go through and do this thing then. Okay, so here, Okay, trace states list of that. So oh, right. So this is, in fact, this is our state event function for the case of, you know what I'm saying? Mm-hmm. Those are our event functions.
Right.
I think we're going to have to insert okay, well, let's move these. Actually, let's put those back. And then this is generating traced evolution. Okay, but the state event functions are being inserted. Where the heck are they being inserted? They're being inserted. Where are they? Oh, in this cases thing down here. So the state event function for this is string rewrite events. Of rules and then hash. And then this becomes, for the list case, okay. So now we come back up here, and the traced states list is basically a nest list. Oh, except if we're going to include the step numbers, we have to do that now. See what I'm saying?
Mm-hmm. Right.
So I think if it's a, I mean, we could do that as a fold list, folding over the range, and we'll include #2 if we feel like it. See what I'm saying?
Right.
Let's break that into two cases. Let's do the options pattern. I don't really understand that, but let's just do this. If options pattern, then fold list of what? Of basically oh God, the state event function is not enough. We need to know at each stage, we need the evolution function, right? We need the the right-hand side, which we can construct. The state event function is not giving us the, look, I think we should make the state event function return and include the output.
The complete state, yes.
Okay, all right, so let's change this then. Yeah, I think that's a useless case, honestly, to just give. Do you think we should do it like that? Then we can prune it. Okay, so let's do that. So in the string rewrite event, that's mapping over the string positions. And I think that's a string replace part, isn't it? Well, the alternative is we could go through and post-process. Right, we can post-process all of these by just replacing. You know what? I'm changing my mind about this. Maybe we do need both. Oh, great. Undo doesn't work in that case. State event evolution function. The list of events and results for and successors for a given state. Okay, so then how are we going to do that?
Well, from the evolution function, it's just the right-hand side of the rule unioned with the rest. Sorry, given the event function.
So you're saying we can just give the event function.
I think it's trivial with, it's just, part specifications, right?
No, but the event function is giving something like this.
Yes, so it's the right-hand side of the rule unioned with the rest, which is the second element of each list. And that's just it, isn't it?
It's not union. You take this and you insert it in there.
Yeah.
Okay, so what we're doing here.
Sorry, well, a join, I should have said, but.
Yeah, right. So what we're doing then is in the nest list, I'm just, oh gosh, okay. I mean, let's just write the nest list here, okay? So for each of these, see, it's going to be more complicated if we want to trace the complete causal network. But for each of these, we can take part, basically, oh boy. You see, the problem is it's different for strings and for other things, right?
Mm-hmm.
I think we're going to need a separate function. I think we're going to need to include the state event evolution function.
Okay.
So that means for each of these, we put in.
But only because the strings case is different from the lists case. Otherwise, I think it
Not
is
just the list case. It's different from the it's different from the Wolfram model case, because in the Wolfram model case, you're just hypergraph unioning the right-hand side of the rule with the rest.
Right. So my point is, I think we don't need to break it into a state event function and a state event evolution function. We can just have a whatever the analog of string join is, that let that be a separate function. That's all we're changing in these cases. It's given the right hand side of the rule and the rest, what do you do on those things? In one case, it's a join. In one case, it's a string join.
Yeah, okay, but either way, we're going to have another function in here.
Right, but I think it's overkill to have state event evolution function be a separate thing.
All right, okay, fine. So then what do we want to do? We want to call it state result from event function. That's what it basically is.
I don't know. I still think the right way to do this is to have specify a join, basically specify how substates are joined. That's the only difference.
Okay. 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 Substate joining function. But it's not that. It's not that, because we got the specific prefix suffix notation. See? It's not that.
Well, what's happening is that in the string case, the order matters, and in all the other cases, it doesn't. Well, the string case and the CA case, and everything that's related to that.
I know, but so it isn't just a joining function. It's a.
Well, if we have the rest list be ordered, then in the Wolfram model case and the list, in any case where there isn't ordering, that doesn't matter.
I know, but I mean, what's this function going to take? It's going to take the right-hand side of the rule and, right, it's going to take the right-hand side of the rule and the residue, right?
Mm-hmm.
I think it's a result derivation function, because I don't think it's a general combination function, is it?
Well, I mean, I still think it is. It just happens to be that in some cases it's order dependent, and in some cases it isn't.
Yeah, but it's not going to work with 5 different elements, right? It's only going to work for this one case of reinserting something. What would you call this?
Substate join function, because in the
but
Wolfram,
it's not a general substate joining function.
Well, when the residue is just a list of lists, right? It's all that's going to be is it'll be a union of that.
No, it won't.
For the Wolfram model case.
It won't be an ordinary union. It'll be some complicated union that involves renaming of nodes and things.
Oh, okay, yes, right. I see what you mean.
It's not obvious this is a good idea, because at the stage where we know look, this is a stage where we know what's going on, right?
Mm-hmm.
So there's no reason to break the thing into, well, okay, hold on. What we need to do is to look ahead to see what's going to happen. Oops. Okay, let's look ahead here. Oops, what happens? Okay, evolution plots. What the heck? Okay, I think that's just rendering stuff there. We are going to need a state rendering function. Because that's what all this stuff is about. See what I'm saying?
Mm-hmm.
So I think maybe we have that in later on. Okay, so this is full of all kinds of gunk. What the hell is this? See, this is digging into the traced states list here to pull out the specific positions of characters to go do stuff with. See what I'm saying?
Mm-hmm.
This is complicated. I mean, then we have to untangle this. I'm not sure that it's useful for us both to work on this at the same time, because I think this is
Right.
This is all stuff that is specific to strings here, or lists for that matter.
Right, but there's no generalization of the notion of a character evolution plot.
No, I mean, this evolution plot has things pointing to the specific places where rewrites occurred, but we can't do that for hypergraphs.
That's what I'm saying, that there's no notion of a character rewrite, a character evolution plot for anything other than a string or a list-based.
Right. And the only difference here is that the trace states list is just differently formatted here.
Mm-hmm.
Okay. What's the character evolution causal graph? Character evolution step.
Well, if you're tracking the evolution of each character, which is what the previous plot is doing, then you can define a causal network for where each character is being acted upon.
Right. Well, the analog of that in hypergraph would be nodes.
Right.
So we need something like this, because this is going to be okay. So this would be the hell is that? Why is it so complicated to get just this? This seems like... I think we have to read this code. Okay, let's install just some of the basic stuff here that we've just added. Oh, we might try to do the Wolfram model case. You're saying, okay, can we do the Wolfram model case in...
I have code for it.
Okay, all right, let's do it. Okay, can you send me the code? Up. That's not going to work.
No?
I guarantee that's not going to work.
Okay. There you go.
But subset replace is in a weird context, right?
Mm-hmm. Which is why I don't want to commit this to the function repository right now.
Well, what context is it in? Because we're going to need it here.
You need to do needs graph store backtick and then needs graph store backtick subsets.
Okay. But that's in the system context, right?
What is?
I mean, not that's already shipping with the product.
I believe so.
Okay. News graph store what? Subsets.
Subsets.
Okay. Subset replace, which will be a system function in 12.1. Okay.
Should I let Tony know that we're planning to do that?
I hope so. Yeah, I thought he knew, but maybe not.
I genuinely don't know what's happening with the subsets stuff.
Yeah, well, so we just need to ask.
Okay, I'll let him know.
Okay. Okay, so when you say multi-way step here,
Yes. That is saying, given a list of rules and an initial condition, for if you just evolve one step, what are all of the possible macroscopic states?
I know, but so that is called a state evolution function.
Right. That's what I'm. Yeah.
Okay, so this is Wolfram model state evolution function. Which does need to be cleaned up because it could be an actual Wolfram model that's in there. Okay. Okay, drum roll here. Okay, what is the state evolution function?
Well, my thing is already doing a catenate, so I think it is just Wolfram model state evolution function.
Okay, the state equivalence function is not same Q.
No, it's isomorphic ordered hypergraph Q.
Which is resource function.
Yes.
Okay, drum roll. All right, multi-way system. So let's get a, where do we have a nice, well, here, I can just pick one up from the notable models repository, perhaps. Where would you suggest? Oh, did you have one here? Oh, but listen, this isn't, this is a pattern rule.
Yes.
Well, you shouldn't have to use those. Right? It should just be zeros and ones. I mean, or whatever.
Right, but
it shouldn't need to be a pattern.
Okay, yeah. The only issue was I was not using any of the Wolfram model code, so I didn't have the from pattern rules or any of that.
Well, so we need to construct this then for using your code.
Mm-hmm.
So what do we need to do to construct that?
I believe Max has a function, but the name keeps changing, so I didn't use it.
Well, I used to have a function that did this, but I mean, from a long time ago, but do we have to rewrite it? Well, I mean, for right now, can you send me, oh yeah, you did send me this. Did this have a title?
I
think not. Oh, it said nifty and it was a bitmap. So that wasn't very
good. Yeah, I can send you the actual rule. Or I don't know.
Yeah, send me the actual rule. You can send that in
Well, hang on, here's the rule and initial condition.
Okay. Okay, there's the rule, there's the initial condition. And then I want to say like 2 steps or something, right? Splarf. Okay. Catenate died. So up here.
Well, hang on, this Wolfram model evolution function didn't evaluate. It looks like.
Well, that's because that should be a list.
Right.
There's another level of list there. Okay.
That looks plausible.
So let's try doing the predecessor thing. So that would be state graph labels, arrow something or another. Hold on, let's do, or we could say predecessor rules list to begin with, and then we'll say states graph. Who knows? Hard to tell.
Well, at least for the first two, it's right.
That's quite entertaining. Look at that bizarre thing of how it renders the hypergraphs. Now, we could actually tell it to render those hypergraphs, couldn't we?
Right.
But let's just, for the hell of it, let's try doing this for 3.
Interesting.
It's kind of wild. Yeah, I think we want to try and put in something which does an arbitrary rendering. So this is, let me just look at how this works. This is element rendering functions. State graph labels. Hunkadorasaurus. Look at that. Well, that's our first multi-way. Nicely displayed. So that is the graph version of multi-way evolution for a hypergraph rewriter, right? Mm-hmm. So the state graph labels let's see if we can say func. Apply the function func to the name of the node. Okay, so this is state graph labels. But vertex shape function, I don't understand how this works, because isn't a vertex shape function applied to the name? Oh, God. Look at this.
We need additional data about the size.
Well, you need to tell it the size. Well, let's just see what happens if we say, okay, so V is the vertex name, so it's #2. What do we do here? We'd have to make an inset, wouldn't we? I think that's right. I think we'd make an inset. Okay, so well, how do we get ordered hypergraph plot? Do I have to, is that already here present? Actually, I'm now curious just what this does if we do 6 steps, for example. That's really quite nice. I don't know what this particular rule is doing, but do you know what this particular rule does?
I don't know. It's one that you sent to me.
Oh, well, maybe it does something interesting.
When I was asking for examples of non-trivial multi-way systems to evolve, it was an example that you sent.
So basically, this is showing us, I mean, this isn't a layered graph plot. I guess we can make this into a layered graph, layered.
I was going to say, yeah.
Layered
Makes more
graph
sense
plot.
as a layered graph plot.
Well, we don't know it picked the right node. Oh my God, that's really funky over there. Well, it may not have picked the right node for the layering.
What happens if you call simple graph of that? I just want to see it without so much looping.
I can't do that because we'd have to do simple graph of the previous
okay.
graph. But I mean, let's see. Doesn't layered graph plot, I think, may allow you to give the node. I thought there was a way of specifying which the initial node is. Okay, so that's the graph there. So we can say of simple graph, what on earth does this mean? I mean, so assume that this is actually the multi-way graph. So we're seeing, I mean, this has no dependence on updating orders, obviously. Except now we have to foliate this creature to get each of the possible updating orders.
Well, it's not foliating, it's picking a branch.
Oh, you're right. Whew. This is kind of complicated. But so what's non-trivial here? Gosh. I mean, if there was causal invariance, then we would see certain features of this multi-way system.
Yeah. You would see anywhere where there's a bifurcation, there's eventually a reconvergence. Which I think actually is true for this one. I think I
Okay.
at least showed that up to some large number of evolution steps.
Well, it's probably just as well that it isn't too simple, because if it was simple, it certainly isn't related to the universe, so to speak.
Right.
It's going to be non-trivial to analyze these things.
Mm-hmm.
Hopefully there are some simple tractable cases that will allow one to understand sort of what's going on.
Right.
This is really quite complicated.
Right. But at least one nice feature of them is that just by looking at the combinatorial structure, we can work out details about causal invariance without having to compute, isomorphisms between causal networks and things.
Yeah, but these are going to get very big very quickly. I mean, this is the Hilbert space of the universe, so to speak.
Right. Right.
It's probably really late for you, so you should probably go. But
yep.
Okay, so let's just agree what's going to happen here. Are you going to try to look at unscrambling the next few steps in this multi-way adventure?
If I can get more tangible information about what that means, then yes.
Well, it just means going through all the other functions we have here and making them work for, and knitting in the Wolfram model code.
Okay, I can do that, but yeah. My only concern is because I didn't write the code that's already there, I'm just going to be tempted to rewrite it.
Well, you don't need to rewrite all of it. There's pieces that will need to be rewritten, yes, because they're being refactored. Look, this is now the third writing, because I wrote the original version, Max wrote a version, and now you're going to write a version.
Yep, okay, that sounds efficient.
Well, it's because we didn't figure out what to do at the beginning, right? And I mean, the question is, I hope we have enough information to reconstruct the causal graph from these state event functions. Do we? Because that character level, what's that?
I think so. Because you know what the rule was, you know where it was applied. So it's just a question of determining overlaps between inputs and outputs for different times.
Okay.
I think.
Right. So in this case, by the way, what we expect to have happen is this is a good approximation to the state. By the way, I think this is the evolution graph for a hypergraph rewriting system, right? Because the other one, the evolution plot, is really pretty specialized to strings.
Mm-hmm.
The only thing that's going to have to be rewritten in that is that we've changed the format of the. Okay, so the issue there, look, the ultimate issue is that we've changed see here, element-wise evolution causal graph. Okay, that's showing each event. And we've changed the format of those events. It's not a big deal, but we've changed the format of the events.
Mm-hmm.
Okay, so the vertex labels, the whole point is that we now have a specification for an event that looks different from this.
Right, but they're trivially interconvertible, at least in the direction we need, because the part specification is given by the rest list and the rule is given by,
well, so we could probably hack this in very quickly, is what you're saying. We could probably,
I think so. I mean, I think so. Like I said, I mean, I don't know how the current code works, but given the specification of vertices that I see there, we can reconstruct that.
Yeah, but the whole point is we don't want the vertices coming out with that form. We want to actually use the current. Okay, right. So look, this is the causal graph. What the hell is this? Element-wise evolution causal graph. See, look at this. Look at this. This is something different. This has both events. I think you just got to look at this code. I'm sorry. Yeah. Okay, so this is in Multiway Systems 04. Okay, I mean I can copy all this code. Can copy this code into here. Yeah, so that's the form we're going to use when we have a step number as well.
Mm-hmm.
All right, you better go. I better go. Let's see if Max can produce the ordered hypergraph plot. I have to say, this is a little bit, I mean, this is scarily complicated. But right. I guess that's the way it goes. Okay, all right. What's that?
It's good. I don't think we have a hope of reproducing quantum field theory if we have simple multi-way systems.
Well, I agree with that, but I haven't yet really wrapped my head around what it means. By the way, the one thing, if you want to go look at fancy stuff, I mean, the, you know, the stuff of Grothendieck's that claims to be, imagine that you have a rewrite system, and now you generate the equivalence class of proofs of a given proposition in the rewrite system.
Right.
Okay. Then you take, and this is something that is somehow comes up in type theory. And then you take the, let's see, let's see, then you look at, what is it? The equivalences. So one thing is the equivalences. Yeah. First, it's the equivalences between this expression and that expression. Then it's the equivalences between proofs for a given expression. And then somehow you look at the equivalences between proofs.
Right, and you get an infinity groupoid.
Do you understand that stuff?
Yeah, it's in the HOT book.
Okay, is it relevant to what we're doing?
Probably. In the sense that my conjecture is that there will end up being deep correspondences between quantum mechanics and automated theorem proving.
Well, I understand that, but I'm asking the question, like the Grothendieck thing, what is the structure that's getting built there? In other words, as we go to these equivalence classes, what we're saying is is causal invariance some kind of equivalence statement about paths in a multi-way system?
Yeah.
And then what's the higher order analog of that?
Well, so I don't know, my interpretation of what's going on is that each observer defines that equivalence, and they may not define it in the same way. So the next layer of the infinity groupoid is some equivalence class between observers.
Yeah.
And so on.
Well, what's the and so on?
I don't know. It starts to look very theological after a little while.
I agree that an equivalence class between observers is an interesting thing, which is the next level up here.
I think so, given an interpretation of quantum mechanics in which an observer defines equivalence classes between multi-way branches.
All right. Well, much as it would be fun to go on with this, I think we probably should wrap here. And I got to go and work on some much more boring things, which I don't really want to work on. I'm deeply procrastinating them.
Sounds good.
It
would be worth looking into whether anyone has formulated a kind of hierarchy of observers in quantum mechanics. I'm not aware of any such thing, but it may exist.
Oh, people have written all kinds of stuff about quantum mechanics, most of which we'll never understand.
Okay, but if there's anything connected to the infinity groupoid, we should look out for it.
Yeah, but the equivalence class, I don't quite understand the whole hierarchy of equivalence classes here. I mean, I understand. Yeah. Anyway, okay. To be continued.
All right.
Okay. See ya. Bye.